section 16.7, surface integrals. In this section, we'll study surface integrals of the form for scalar functions and for vector fields. For vector fields, we take only the normal components so that f dot n becomes a scalar function. We'll deal with this one in the second part. Let's begin with surface integrals of scalar functions. The surface is parameterized by R of uv, uv in D. Then we know from the previous section, ds becomes the length of r sub u cross r sub v dA. So this integral with a scalar function x can be written in this way. For xyz, we express this function as a function of uv, and this length is the scaling factor. And this is the calculation formula. Particularly when the surface is made with this explicit function z equal g of xy, then r sub x cross r sub y will be minus g sub x, minus g sub y, and 1. You may think of this one in this way. Anyway, that one is normal vector. So from here, you may consider z minus g of xy equals 0. Then this can be considered as a level surface. And for the level surface, you can get the gradient. Then that will be the normal vector. So that is, first one is minus g sub x. Second, y derivative is minus g sub y. And z derivative is 1. So you may think, you may try to memorize this one along with that mathematics. Okay. Once we get this cross product, measured length easily, so that for this special case, you can get the surface integral of the scalar function in this way. Okay. And that is quite similar for the line integral. Now, for curve in 3D, there is curve integral along with arc length segment. Then ds, this is small s, little s, that is the same as r prime magnitude dt. And you can get the integral from a to b of this scalar function as a function of t. Okay, it's quite similar. Okay. Okay, here we have a problem. Compute the surface integral, double integral over s xy ds, where s is the triangular region with the vertices 1, 0, 0, 0, 2, 0, 0, 0, 2. Okay, so let's try to visualize the surface. That is x, y, z coordinate. That is x direction. That is y direction. And that is z direction. In x direction, the intercept is 1. And y direction is 2. And z direction again 2. So that this triangle cut is the surface S. Right? Okay, that is S. Okay. Now, the surface can be expressed as here, x is 1, y is 2, z is 2, and equals 1. Right? Then after multiplying 2, and we rearrange it to get that one. Now, for the surface integral, the given integral will be double integral over d. Of course, you can find D quite easily once you consider this one as a function of this is a representation, then the bottom must be D. Right? Okay, same in x and y, and you have to put here square root of g sub x squared plus g sub y squared plus 1 dA. Right? Okay, let's try to get this one. Okay, the scaling factor is g sub x. Okay, x derivative is -2, squared is 4, y derivative is -1, squared is 1, and plus 1, so that is square root of 6. So here, the given integral is same as now square root of 6 is constant. It can be out of the integral and xy dA. Now we have to access D systematically. Okay, let's try to visualize D. Okay, that is D. Then x direction and y direction. In x direction is 1, and y direction, okay, that is 2. And this one, that is that equation is y equal to minus 2x, right? Slope is -2, the intercept is 2, so 2 minus 2x. Okay, so here, the constant, square root of 6, and if x is the outer integral, then x will move from 0 to 1, right? That is 0 to 1, x is moving. For each x, in y direction, vertically, bottom y is 0, top y is on the line, right? So that is 0 to top y is 2 minus 2x, the line. Okay, that is now xy and dy and dx. Okay, so that is same as square root of 6 of the outer integral. And for inner integral, we can make now x and y becomes half y squared. It's antiderivative. And we are evaluating from 0 to 2 minus 2x. Right? Okay. Now half can go out, and that is square root of 6 over 2. And that is now, if you evaluate, then that is 2 minus 2x squared. So that 2 can go out to become 4. Okay, let's put 4 outside, and from 0 to 1, and that is x and 1 minus x squared. Okay. Then for that one, okay, we have to get the integral. But for this one, okay, let's try to expand that. Then that is x cubed minus 2x, so that minus 2x squared, and plus 1, so plus x. Okay, that is now 2 square root of 6 times. Okay, here from this one, you will have 1/4. From this one, you will have 2 over 3. From this one, you'll have 1/2, right? If you simplify, then you'll get the answer. That must be 1 over square root of 6, right? Okay, now we see another problem. Okay, evaluate double integral, surface integral of z ds, where S is the surface whose side S1 is given by here, and whose bottom S2 is the disk in the plane, so the bottom plane, whose top S3 is disk of radius 1 in the plane z equals 1. So it is a cylinder, and z direction is from 0 to 1. Right? Okay, let's try to visualize the surface. X and Y and Z, and now this is a cylinder, vertical cylinder with a radius 1 in circular region, and there's height is 1, so that radius 1 and there's height is 1. So here side is S1, bottom is S2, top is S3. Okay, so we have to get the surface integral piece by piece, because we can make representation, parametric representation piece by piece, so that we'll try to get the integral piece by piece. Let's begin with S1. S1 as given here. Now in xy direction is a circular, so that x is cosine theta, y is sine theta. Okay, we'll try to use that. Z is z. So it's that is r. Now theta is a variable, z is another one, and x direction is cosine theta, and y direction sine theta, and z component is z. Okay, and then now theta and z, that one must be, theta must be from 0 to 2 pi, whole circulation, and z is from 0 to 1. We have cylinder of height 1, so it's from 0 to 1. Okay, that is a parameterization of side. Okay, for that one, we have to use the formula. Okay, let's see the formula. That is now r sub u plus r sub v. We have to get that one. Let's go back to the formula and try to use that. That is for surface integral of scalar function. We have now integral over the and this scaling factor. Okay, we have to get it. Now this parameterization is theta and z based on these two variables. So we have to get r theta and r z. Okay, that one is minus sine theta and cosine theta, and z is another independent variable, so must be 0. Now r sub z, okay, that one, these are independent of z, so that's 0, 0, and last one is 1. Right? Okay, then from this one, we have to get the cross product, r sub theta cross r sub z. Okay, now in your mind, you may think the metric, you have to get determinant of a metric, that one, and you may think here I, j, k, the top row, this is second and third row. You may think of that way. Okay, with that metric, we have to get the determinant. For I, we have this minus that is cosine theta. For j, you have that 0 minus sine theta. So that must be sine theta. For the last one, k, okay, bottom is 0, so it is 0. So from here, quite easily we can see r theta cross r z, that one equals 1. Anyway, this one is scaling factor of area. For example, here, this is area is 2 pi, but for this one, if you try to measure area of the side, then it's again 2 pi, which means that the scaling factor must be 1. If you don't have time, then just try to compare the area, and then you can decide this quantity quite easily. It must be 1 for this example. Okay. Okay. Along with this scaling factor, double integral over S1 and z ds, that must be integral over d, and we have to put z is now the z itself, and now that is the theta dc. Right? Theta is moving from 0 to 2 pi, z is moving from 0 to 1, and z dz d theta. That'll make a half, and 2 pi, so that must be pi. Okay. Now, we'll move on to S2. Okay, on S2, the integrand is 0, z equals 0, right? So that clearly this integral must be 0. S2 z, which is 0, so that must be 0, right? So we can get it quite easily. How about S3? Then it's a flat top, and where z is 1, so that surface integral over S3 z ds, this is 1, so that eventually the output, the result must be area of this top. This is a disk of radius 1, so that pi r squared, r is 1, so that must be pi. By summing this three quantity, we can conclude the answer is now 2 pi. Right? Okay. Okay, we'll continue in the second part. Thank you.